Before we begin, if everyone doesn't mind turning off their webcams, so that what we like to do is only one person have their webcam on at a time to draw attention to the speaker. So, yeah, just if at all possible, turn off your webcam. Thank you.
Okay. All right, will do.
All right, so I'm going to go ahead and begin. All right, hey everyone, our design project is PDOS. It stands for Power Distribution Optimization System, and it's going to be an added feature for residential building management systems. My name is Alex Kane. I'm a team and battery management system lead, and I'm an electrical engineering student from Coldwater, Mississippi.
My name is Liam Nelson. I'm a generation and simulation lead. I'm an electrical engineering student from Huntsville, Alabama.
My name is Noah Morrison. I'm the microcontroller lead. I'm an electrical engineering student from Madison, Mississippi.
My name is Christopher Jones. I'm the source switching and API lead. I'm a computer engineering student from South Haven, Mississippi.
My name is Thomas Fry. I'm the user interface lead, and I'm a computer engineer from Jackson, Mississippi. And our team advisor is Dr. Jumbo Zhao. He's an assistant professor at Mississippi State University from the ECE department.
First, we're going to go through our project outline. So first, we're going to go through our project or problem and solution and how PDOS addresses problems in our current market. Next, we're going to cover design constraints. And then we're going to cover testing and how we tested our system functionally. And then we're going to go over our completed and future milestones. And then we're going to cover our conclusion. So first, let's start with the problem and solution. So a big problem in the residential market today is there are no market-ready options for home energy management. You'll see lots of homes that have solar panels and they have battery storage, but they have no way to properly manage these assets. And even though they have these assets, you will often see people paying premium prices for grid power because this battery storage drains when power is cheap. And then when power is expensive, their batteries are completely drained and they have no way, and then they're forced to purchase this expensive grid power. So also, in the event of inclement weather, sometimes homeowners with solar and battery storage are not prepared for those events either, because the battery will be drained by the time the storm approaches. Our solution is PDOS. PDOS does not allow the battery to discharge when grid prices are low, and it also will detect future inclement weather, and then it will make sure that the battery is fully charged when this event starts. PDOS further incentivizes purchasing solar and battery storage by saving the homeowner more money over time and ensuring the homeowner is as prepared as possible for inclement weather events.
Okay, so I'm going to take us through some of our core design constraints. Our first is technical constraints. We have power supply, which is the power supply input for the battery management system. It needs to be 9-volt DC from a wall converter, step down to a 4-volt to supply the battery. And we also have the battery supply, that battery life, which PDOS ensures that the battery cuts off at 25% capacity to reduce battery degradation. We also have forecast and grid pricing data, which we acquire from online APIs like OpenWeather and OpenEI to implement into our product. And we have solar panel inverter, which the solar panel inverter should output 120 VAC, and the voltage fluctuation should be between 10%. We have surge protection, where the battery management system utilizes multiple relays to detect power surges and disconnects the circuit to prevent equipment damage. We also have power output switching, where PDOS determines the most optimal power supply and can switch between solar, grid, and battery power. And then a few of our core practical constraints, we have economic. PDOS ensures that the cost of using solar and battery power is more cost effective than using only grid power. And we also have environmental. PDOS utilizes renewable power, such as solar and battery. Solar battery power is charged from solar to create a green energy solution for residential homes. And then our energy engineering standards, we have IEEE 82.11, which is the standard that defines wireless networking protocol for the Wi-Fi interfacing microcontroller. And we have IEEE 2030.5, which is the inverter configuration for to specify the inverter outputs. And we have the JSON API, which is a data format specification for HTTP GET request and REST APIs. And now we're going to do a quick recap of our approach. We have our system overview, which the Arduino is the main component. It has 3 subsystems connected to it, one being the battery management system, 2 being the node MCU and API data, and then the last one being the energy plus inputs. And now we're going to do an overview of our generation algorithms. The solar and radiance values will be given from energy plus and open weather, and that'll output our true solar output for source switching. And we'll also get our battery values from battery management system, which will give us our state of charge. And then we'll get our grid values from OpenEI, which will give us our power price. Those values will go into our source switching algorithm, where the source switching will determine if the solar output threshold is met. If it is met, solar slot number 1 will be solar, and if demand is met, slot number 2 is empty. And then we'll check load against demand over and over until it is not. And if solar output threshold is not met, we'll check battery, and if battery is above 25% and there is no inclement weather, then we'll check to see if slot number 1 is filled, and if it's not, battery will be number 1, and if demand is met, slot is number 2, and it'll be vice versa for grid power, solar power, and battery all through.
Now I'm going to take you through some of the testing for each of our subsystems. For the battery management system, it consists of a charging system, a discharging subsystem, and surge protection. For the charging system, the first thing that was tested was the power supply. We had to ensure the power supply was outputting the correct 9 volts. Then we connected to the buck converter and made sure it was outputting 4 volts. Next, we ran through the entire charging subsystem to make sure the LCD screen was outputting each display that we wanted. And we also ran through the discharging subsystem to make sure it was outputting the correct power percentage on the screen. Then we ran the entire system with the battery. We discharged at 3.4 volts, connected it to our system, and charged it all the way up to 4. Once our current limit was reached, which is 0.2, the relay disconnects because the battery is fully charged. So we disconnected the battery from our system, checked it with a multimeter, and the battery read 4 volts. Therefore, our entire system passed. For the discharging subsystem, we don't want the battery to go below 25% capacity. The Arduino reads the current voltage from the battery, and if that current voltage is less than or equal to the voltage limit we set, that is 25%, the relay for the discharging power supply will disconnect, and the circuit will disconnect, and the discharger can't discharge the battery any longer. And in our algorithms, we have the battery cannot be used as a power slot until it reaches 35%. And once it reaches 35%, it can be used as a power slot and the discharge can work again. And then one of the most important things in our battery management system is the surge protection. If you look at this little black box in the picture, that's our relay for the charging system. And that disconnects the circuit if overcurrent is detected, undercurrent is detected, and reverse current is detected. And we test our circuit against all these, and each time one of these events happened, the relay disconnected the circuit, and the battery was saved from any further damage.
So for data integration testing, we're looking at the OpenWeather and OpenEI API data that we're pulling. Then we're looking at the Energy Plus simulation data and communication between our 2 microcontrollers. And finally, we're discussing the user interface that brings all this data together. Starting with the OpenWeather API, we see a snapshot of our data request to the OpenWeather server and the response that it returns. For the sake of the picture, we've cut off the full data set, but you can see based on the scroll bar at the bottom, it's pretty large. Once we've received that data, we parse it for information we'd like to pass on to the Arduino and our web server. At the bottom of the screen, you can see the cloud, temperature, alerts, and alert start time reserialized and available to use dynamically. Immediately after finishing our OpenWeather process, we do the same thing with our grid pricing data. This is an extremely large data set where we pull down hourly grid pricing data for the entire year. Here we can see small snippets of the hourly tiers and the pricing rates for those tiers. At the bottom right, we again show the data we're extracting from this set and sending to both the Arduino and the web server. Our Energy Plus data is calculated in a simulation that runs yearly test cases for our model home in Windows. Once we have this data, it's loaded onto an SD card and read in at the very beginning of the Arduino cycle. Here we can see the serial feedback of some of the solar data being read in for the summer and winter test cases. As you can see, we have 0 solar output in early morning and late evening hours, with the output ramping up and down around the peak values in the early afternoon. For PDOS to work correctly, we have to have constant communication between our two microcontrollers. This is a process that involves repeated deserialization and reserialization, or unpackaging and repackaging of our data sets. The Arduino listens for communication from the node while the node receives the server data that we saw previously, and the node listens for communication back from the Arduino while it processes our calculations on the data. We were able to successfully package our data and send it through the UART serial communication. Here we see some examples of those data transactions. On the top left and bottom left, we have our final calculation data being sent from the Arduino. You can see that our power slots, solar radiance, grid pricing, and battery charge data are successfully sent from one controller to the other. On the right, we have the Arduino serial output for the OpenWeather and OpenEI datasets that we showed earlier. You can see that we received the serialized data completely intact and are able to store it into variables for our calculations. And finally, we have the user interface for our system. The last process in our system is to take the data we've calculated and push it dynamically to an updating private web server. Around every 15 seconds, a request is made to the server that updates the values in each of these pages.
Okay, so I'll take you through the algorithms testing section. First off, we're going to go through our generation algorithm, basically the inputs that we get from our models, then the source switching algorithm, and lastly, the power output switching device that we've put physically in our hardware that would set all the LEDs. So for solar irradiance, this is our first input value that we gather from our generation algorithm. We take the inputs from the Energy Plus model and parse them through our algorithm. And what we get is the expected input value and data that we expect. And when we put it through our algorithm, we got we received the actual output that we were expecting, and that passed the test. Our values are also scalable for our 3.7 volt battery that we're currently using for our product. The same applies to grid pricing, but instead of through the Energy Plus, we're doing it through our Open Energy Information API, and we are pulling down values based on different grid tiers and prices, and we are taking those expected values and putting them through our algorithm. What we got were what we expected, and so they would all pass those tests. And lastly, for our source switching algorithm, what we would get through our power slots, we would take all the input data that was gathered from our generation algorithms and would then test it through this big function that would determine what power sources are best used or be optimized for that current situation. For example, we would take for the solar output, it being very large at the top, and with battery charge percentage being at 45 and no inclement weather being present, we would be placing the solar power source in the first power slot, and we would leave nothing in the power slot 2 because it was not needed due to the solar wattage being so high. And in case there is no solar output, let's say on like a cloudy day, and there's no inclement weather present, but the battery is decently charged, we would put the battery in the first power slot and leave the second power slot empty due to having no use for it currently. And in case battery is low and there's no inclement weather as well as no solar output wattage, we would put grid as the primary power slot. Secondary power slots would be available depending on the situation that's currently affecting the household. And lastly, this is what we have physically, and as a part of our hardware, we use a series of relays that would simulate our test data. That is accurate to it, and it will, and different LEDs would flash on and off depending on the type of power slots that are currently inhabiting the slots. And so our green LED would be solar, our blue one would be battery, and our red one would be grid. As you can see in these pictures, we have solar output with in the first slot with nothing attached to it. And then second picture would be solar with the grid, and the last one would be battery with the grid.
So our progress so far on this project, we have ordered all of our microcontroller parts. We have the Energy Plus model up and working. We have all the API data pooled. The battery management system is completely built and functional, as well as all of the algorithms are complete. We also have done Energy Plus data. We have input that into the SD card and sent that data over to the Arduino, and we have completed the web page. At this point, we are now working on the November 30th deadline. For future plans, we want to think about maybe doing an enclosure. We want to maybe implement into an actual building management system. We might want to add RTOS functionality. And we may end up using a real solar panel to generate real solar data and have it react to that. For a conclusion, PDOS is resilient and it ensures homeowners have emergency power in the case of severe weather. It's environmentally friendly and optimizes the use of solar and battery power over grid power. It's grid supportive and supports the local grid by not using power during peak hours of the day. And it's cost effective and it saves homeowners money by using less grid power during peak times. And now we'll move it over to the art students and allow them to present their project.
I'm sorry, I'm figuring out how to share my screen.
Amy, are you still there? Your screen looks a little frozen.
Yeah, I think she froze. Can you start, Emily? Maybe can you share?
Yes, 1 second. I have to figure out how to share too. I have no idea.
It's on the top, right?
Yeah, the top right, there's a box with an arrow in it.
Arrow, upward arrow next to leave.
Emily, I'm back if you want me to share it since I have the video. Sorry,
Okay.
don't know what happened. Okay.
Amy, your screen looks a little frozen. Not seeing anything.
Oh, is it not moving?
No.
Can y'all see that now?
I don't see anything.
I don't see either.
I can see now.
Okay, maybe with a little delay, everybody can see. Okay.
Okay. Is it working now?
Not for me.
Not for me either.
What is going on? Emily, do you want to try?
Yeah, I can try. I just don't have the ending part, you know.
That's okay. You can start.
Okay.
By the time she can fix hers. Amy, in the meantime, can you leave this and again, come back to the Teams meeting again?
Yes, I'm gonna go fix this, but I'll be back.
Okay, yeah.
And it's just showing a circle.
Yeah, it's the internet problem. Yeah, it is slow today. So maybe where you are, it must have been much lower.
Yeah, my apartment doesn't have the best Wi-Fi.
Okay, in the meantime, guys, the PDOS, I think you have completed, okay, you've done everything. So
Yeah, it's still not doing anything for me.
I guess we
Yeah.
I guess we could field questions while they're working on their issues.
I wonder, graphic designs team, if you could email your presentation real quick with one of our students, and then they could flip through your slides for you. That might work. Could be worth a shot.
Amy,
I'll send it. I just hope the video works.
Yeah, you can send it to Alex Kane.
Okay.
Did you try it again, Amy?
Let me try one more time.
At least you're back.
yeah,
around.
Yeah, she's not frozen anymore.
Oh,
oh, there it is. Okay,
I got it.
We're back in business.
Okay. If it'll let me full screen this, maybe. Oh well, I guess it won't let me full screen. Are y'all ready?
Ready when you are.
Okay. So I'm Amy Kloss. If y'all want to introduce yourselves too.
I'm Emily.
Spencer, I think you're muted.
You're correct. I'm sorry about that. My name is Spencer Thomas.
So we're the graphic design team for PDOS. But so basically, about project, we you already know all about this project from the boys' presentation, but our goal was basically just to create this sleek, simple visual design, mostly because this product is a it's for display, it's for people to use, and so we just wanted to make it look nice, basically. But to start off, Emily's going to talk about our logo and color palette.
Hello. So I was going to start us off with the color palette. So this logo was actually made by our partners originally, and where we just took it a little bit further and just made a few different color variations. So these color variations are shown in the light and dark mode that are on the device, which Amy's going to talk about a little bit later. And now I'm going to move on to the color palette. So for our color palette, we started off with the teal and the gray from the original logo that was given to us, and we ended up making a few different shades of that teal that we were given. But in order to kind of steer away from that monochromatic feel, we wanted to, just throw in some orange shades to give it a bit of a contrast with the blues. And now I'm going to hand it back over to Amy to talk about the icons.
Okay, so these are the icons that we created for the whole device. To start with the upper left, these are the main icons that are kind of on the home menu page. They kind of take you to each different section of the product. Underneath that is the home icon, which kind of derives from the logo a little bit. We just kind of took it apart, but that's on every page just to go back to the main menu. On the top right is the weather icons, and these appear on the weather tabs below that to give you the forecast throughout the week. And then in the middle, kind of near the bottom, are the settings tab icons, which is on the main icon page. And this is just, a couple little things in our settings page, but basically the whole design of this was inspired by the teal logo and obviously the color palette. But everything that you see here came from the color palette, and now Spencer's going to talk about the typeface that we also incorporated into this.
Hi guys, yes, for our typeface, we chose a sans serif type called Sri Devangari 714. We've shown an alphabet with upper and lowercase and the numerals, as well as different point sizes, just to give a just kind of an overview of the type and how it looks on the screen. It's simple. It gave us some options. It's not too distracting from either the logos or the main icon, and it worked out pretty well for us. And back to Emily for some navigation.
Yeah, so our navigation is really simple throughout the whole device. It's super straightforward. The home button that is circled right there can take you back to the main menu at any time on any page. So that's kind of it for the device. Super simple and sleek, straightforward. So now Amy's going to talk about the display.
So these are just a couple of screen caps from the product prototype. But another aspect of our display is that we put this gradient behind everything to kind of make it pop and feel less flat. Obviously, we have a good amount of colors to work with, but I think this gradient helped us a lot in filling some blank areas and just creating some nice depth in the product. But next, Spencer's going to talk about our wireframe.
Okay, so our wireframe, it's just going to show you our simple sequence of events, from the dissolve screen down to our actual tabs you go to from the home screen. This is just a static image of the movement from each button to where they go. And I believe we have a video showing just a little more up close view of how this works. So on to that video. And it'll start at the loading screen with our animated icon, and it brings us to our home screen where we have our settings tab where you can change it from light to dark mode. Also a help tab. And we'll go back to the home page and check out our battery power. Then I'll bring you to our battery page, and it'll let you know the information there, as well as each tab bringing you to the information you need to get to. Solar power as well. We have their power grid coming up next, which each of the power sources that they have discussed, the solar, the battery, and the grid can show up in these power slots. And then for a weather forecast, we'll show a week's worth of time, but you can also click on the day and have a full day's worth of weather. So that will help with any of the solar and time for using of the battery, plus a weather degree section just for some temperature and just simple, easy navigation. And that is our prototype right there.
All right, that is a nice looking app, guys. I'm afraid we're out of time, so we got to wrap this up real quick. But thank y'all so much for sharing that app with us. That looks really good. I like that color palette.
And I like the icons too. And good presentation, guys, from senior design team and the graphic design team. Excellent presentation and excellent add-on interface. Okay. And the senior design team, are you planning to have that user input screen something?
Are you talking about integrating their user interface into the product?
Mm-hmm.
Yes, it's already finished. We've got it fully done.
Oh, okay. Okay, that's good. So on the demo day.
I'm sorry, the screenshots that we posted in our presentation were taken directly from our web server.
Oh, okay. Okay, good. Okay. And also, I mean, we were thinking of on the demo day some user-friendly inputs so that the user can select the temperature or something. Did you do that? Are you planning to do that?
Correct. We're gonna ask users for the data they'd like to input, whether that's going to be temperature, clouds, different things like that, and then we're going to show how that updates through our entire system and updates the pages. We're going to have the user interface on a small touch screen, and you'll be able to navigate it through there.
Excellent. Excellent, guys. Thank you so much. Okay, very nice and smooth presentation. Okay, with a little technical glitch, but that's fine. Okay, that happens for everyone. So.
All right. Well, thank y'all, guys.
I appreciate it.
Thank y'all.
Thank you all.
Thank you.
Bye-bye.
Thank y'all.
Good job. Thank you.